One thing which is emerged from so many blowing is that the blowing is basically supposed to the foundation stone of the campaign life. So this first 12 hours activity becomes a very vital for this campaign extension of the blast furnace also. And that's why this presentation is very important regarding the thermal ignition. So today we are breaking down the industrial blueprint to thermal ignition. Our screen, as you can see, the master blueprint, a technical cross section of furnace shell in a dark slate gray, overlaid with a precise white line architectural grid. This represents our roadmap for the critical below the mental engineering. By end of this session, we will gain three specific deliverables. So basically all these three deliverables are like this: that first, the exact fabrication geometry for the blowout pipe that prevents clogging. Second, the structural physics of the doghouse foundation. And third, the diagnostic timeline for the sputtering phase. So we are not just lighting a fire, we are engineering a thermal breeze into the deep hearth. So to build that bridge, we must first define the three fundamental objectives of our thermal pathway. So coming to the thermal pathway engineering. So look at the thermal map on the right. You will see the furnace profile with the bright arrows indicating the hot blast entry point, the TUS. Notice the large orange to yellow clumps of the head that the raceway. That's the raceway. The primary objective, as stated in the top left box, is to force heat transfer from that raceway directly into the deep hearth using our pipe as bypass channel. Without these, the deadman remains a cold, inert mass that could freeze your first cast. Structurally, we are protecting the lower infrastructure from the initial blast impact, while operationally, we are setting the stage for controlled liquid extraction. The so what factor is simple. If you fail to engineer this pathway, you will have a hearth full of chilled iron that require weeks of lancing to recover, costing millions in lost productivity and fuel. So establishing this thermal flow requires a robust internal structure to protect our hardware from the burden's weight. And similarly, as we discussed earlier, the doghouse architecture and engineering become one of our very important aspects. So on your screen is isometric exploded view of the doghouse, as you can see. The start at the bottom, layer 1 is 20 centimeter leveling bed of a standard blast furnace slag. Above that, layer 2 shows a 3 multiplied by 3 multiplied by 3 meter cubic void protector, essentially wooden fortress. Finally, layer 3 shows the heavy railway sleeper, specifically 200 to 300 millimeter wide and up to 2.5 meter long, stacked in a cross hatch pattern. The key directive box in the bottom right is critical. The doghouse serves strictly as a physical shield. It maintains an open void for the blowout pipes during the initial burden descent. If this structure is built incorrectly or collapse, the heavy burden will crush your pipe, cutting off your thermal bridge. The operational impact will be severe, a cold hearth and an immediate high-risk delay in your blow-in schedule. So while the doghouse protects the pipe, we need a large scaffold to maintain the incoming fuel. So the temporary scaffold is like this. This cross section shows the lower furnace in a dark navy blue grid. Notice the cyan dashed line, that's our target fill level, our platform exactly 1 meter above the tier. So we surround the doghouse with a fill zone of dry waste wood and mainly this. Uh, the so what here is not about the wood's calorific value, it's about the physics of coke blank. So look at the orange box titled the physics. The wood act as a mechanical shelf holding the initial coke blank above the tier. This forces every single piece of descending coke to pass strictly through the active coke zone, maximizing the heat generation and driving the thermal mass deep into the hearth. This engineered delay ensures that then when the coke finally reaches the bottom, it is superheated, providing the thermal energy needed to keep the hearth liquid fluid. Now that's the environment prepared. So let's look at a specific engineering of pipe themselves. Blowout pipe engineering anatomy. Here is the mechanical heart of our setup. The diagram shows that the 4-inch scheduled 40 carbon steel pipe penetrating the furnace wall. Take note of internal reach. The pipe must terminate exactly 100 millimeter from the furnace center. Look at the call out for the perforation specifications. So these are 15 millimeter dia holes drilled every 200 millimeters space. So there is a critical constraint highlight in orange. Those holes must be located strictly on the bottom and sides. Why? Because it prevents top clogging from descending fines and debris. If you drill hole on the top, the pipe will choke within hours. The operational impact is direct. A properly perforated pipe ensures a steady flow of hot gases into the hearth, while a clogged pipe leaves you blind and cold. A perfect pipe is useless if it is not aligned and sealed correctly against the furnace pressure. Coming to the taphole alignment and the flange integration. So insertion geometry, as you can see on the right, a high detailed 3D render of the mounting interface. The pipe must be inserted at the exact normal taphole angle to ensure it aligns with our launching path later. Notice the 10 millimeter thick 400 millimeter squared carbon steel plate. It is fully welded to the pipe barrel to act as a sealing plate. This plate sits flush against the ABP flange, creating a rigid leak-proof seal. The so what factor here is safety and pressure integrity. During blowing, internal pressure fluctuates wildly. A poor seal at the taphole leads to gas leakage and potential flame cutting of the flange. We need this interface to be bomb-proof to maintain the integrity of our past blast plan. So because of those high internal pressure, we must also secure pipe from the outside. That is that we can see from here as from the slide also. So this is basically we can see the notice of the dual chain rigging system as bright color we have shown, and this chain all these arrangements is being done, that is already in the preceding slide in the shown. So if the pipe is allowed to shift or kick back under pressure, you lose your seal and create a massive safety hazard on the cast floor. And for this, there is a wedge particularly welded with a pipe. So this rigging ensure that our thermal pathway remains exactly where we engineered it to be, regardless of the turbulence inside the furnace. So with everything secured and blast on, we enter the most critical monitoring phase of operation, that is the operational execution and the hearth monitoring. This slide features a clean horizontal timeline moving from a T0 to a growing T12R. So look at the diagnostic note at the bottom. A sputtering is not a malfunction. When you see the blowout pipe exhaust start to sputter, it's your primary physical indicator that slag and iron have successfully accumulated in the deep hearth and reached the pipe's elevation. This is the eureka moment of the blow-in, which tells us the hearth is alive and receiving liquids. The operational impact of missing this signal is severe if you leave the pipe in too long after sputtering start. They will melt our plug completely, making the subsequent taphole opening much more difficult. So once sputtering is confirmed, we begin the high stakes tactical transition to the first cast. So first cast, this four-step flowchart outline the transition. Step 1, monitor the flame. Once it almost stopped, you cut the pipe immediately. We often reduce the blast pressure here for safety. And step 2, as you can see, the taphole, launching the taphole until you see the healthy sustained flame, confirming the connection of the two here. Step 3 is highlighted in the in orange, that is the protect connection. You must plug the taphole using exactly a half strip, regularly 30 liter of the clay. Any more foul the connection we just found to establish. So finally, step 4, execute the first step exactly 1 hour after pipe removal. Use a larger 60 to 65 millimeter drill bit to use it. The so factor here is establishment of a stable tapping rhythm. So get this right and you have successfully transitioned the furnace from a construction project to a production asset. So to ensure to detail it is missed, we provide the final execution matrix for the team. And we will wrap up this with the comprehensive matrix. On the left, we have a fabrication. Remember, um, the 4-inch schedule, 40 steel and bottom only perforation. In the center installation, focus on plus 1 millimeter wood fill and normal taphole angle. On the right, operation the 12-hour sputtering trigger and the 60 millimeter drill bit. So maintain uh, rigid adherence to this dimension. So this matrix is our collective insurance policy against an interrupted thermal transition. If you follow this engineering standard, you ensure the hearth stays hot, the liquid stays fluid, and the furnace begins its campaign with a position of strength.